So let's talk about true stress and strain curves. But before we do that, this is an example of basically stress strain curves here. Here in these stress strain curves, you're looking at basically annealing samples. So this is highly annealed, so the temperature is very high. The time is also very long. These are you can look at these as work hardened as well. So dislocation density is the highest here because my yield stress is the highest as well. Another cool idea or stress strain curve or feature of stress strain curve for metals is a Cottrell atmosphere. So basically for steel, which is composed of iron and carbon, your carbon interstitials will move towards this region of your or near your edge dislocation. Why? You have compression here, you have tension here, lots of space for those atoms to sit in, and you pull your material, you stress it, and then you get this kind of, once you have enough stress to pull away from this Cottrell atmosphere, you get this relaxation because these interstitials, these little carbon atoms, actually make it very difficult to move that dislocation. So you get this dip and then build up again because those atoms will then, again, seek and try to basically pin those edge dislocations. But we'll get to that. We'll get to that feature, and we'll get to kind of the diffusion of essentially interstitial atoms near edge dislocations and the interaction between edge dislocations and other 0D defects in later lectures. But cool feature. All right, true stress strain curves. So we've been dealing with, they're not too common. Most of the time, we're always going to be looking at engineering stress strain curves, but occasionally, especially if you're looking with polymetric materials, true stress strain curves may be of interest. So our definition of engineering stress and strain was force over your original cross-sectional area. And strain, engineering strain, is the same. Change in length over your original length. But if you're trying to describe true stress, you need to divide, actually look at the force over the instantaneous area. Difficult to calculate. But we can try to develop a relationship by invoking a conservation of volume argument. This is a very common argument to make, and we're basically saying as we stress our material, the original length times the initial length, original area times the initial length, the volume. So basically our V naught must be equal to my instantaneous volume. I'm not creating or destroying matter. If we do that, we can use this relationship to rewrite our definition of engineering strain. So I can relate my engineering strain to this A naught over here, and you can do some more math and write out this relationship here. So my true stress over my engineering stress is related to my engineering strain plus 1. So I could rewrite my true stress in terms of my engineering strain, which I know. So I can develop this relationship here. So my true stress is related to engineering stress, which I know, and my engineering strain, which I know. I could do something similar for my true strain is the change in length over my initial, or actually take the integral here, initial length here. So I could get this my true strain would be this function right here, LF over here. I can, again, do some math and do some rewriting, and I could find that my true strain is going to be log plus 1 engineering strain. Again, I know what this value is here. Oftentimes with polymers, you're going to deal with this extension ratio, so L final length over initial length, and you could actually even rewrite your true stress and strain even more simply here. But you can see this, and actually for metals, occasionally you'll see this power law relationship, but that's how I can relate essentially my true stress and true strain. What does that actually look like? So you see here that we match perfectly, and actually you can see this here, and actually you can see that a little bit below. Let's go back over here. So if I look at this relationship here, this is going to be exactly the same up until yielding. So my true stress and my true strain, they're exactly the same up until the point where we yield. And that's where this kind of relationship here, this strain hardening parameter, this N, this parameter here, is going to be important later, but that value will vary. And it's this power law relationship. So materials can strain harden, strain soften, or behave perfectly plastic, as we kind of saw previously. So when I'm describing my yield strength, so basically we're exactly the same up to here, and then once I yield, I can describe this, my yield stress, or what my yield stress may be, as a function of this true strain. So it depends on the strain hardening, perfect plastic, and strain softening as well. So I could describe what that may indeed look like. And you can kind of do it as well. But that parameter here, if it strain hardens, again, my yield strength will increase. Plastic, it'll just be flat. If it's softening, then it'll kind of dip below here. So that is how we can kind of describe essentially the true, or the yields, basically the true stress beyond the yield stress. So this would be effectively that true yield stress. So that is essentially, in a nutshell, how you can relate true stress and strain. You will be asked to do that on a problem set. So again, true stress, true strain, and you'll see we looked exactly similar. You see this, we never see kind of a dip or an increase in here because, and it makes sense, right? From kind of a, I don't want to say phenomenological, but from an intuitive standpoint, the stress should always be increasing. It's always strange when I see stress strain curves where we see kind of this dip, right? Even the neck. Your stress should be building up until it's reaching a breaking point, no pun intended, to where our material actually has to fracture. So the true engineering curve looks a little bit better, but again, from a practicality standpoint, you're going to really see the engineering stress strain curve a lot more often. So you're all experts in the stress strain curve. You can calculate every parameter. You know how to interpret it. You can use it to differentiate between materials. So here's the bad news. We've done all this work for a very, 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 very specific stress state, uniaxial tension, that is not so common. So we are going to need to dive much, much more deeper into the tensorial definition of stress and strain so we can solve much more complex and interesting problems. But again, you'll be ready for that job interview at Intel with this information. So we'll see you all next time, and thanks. Bye.